Welcome everyone to the EasyPower webinar series. My name is Jim Chastain. I'm your host for today's session. And we have joining us as a guest speaker, Mr. Austin Johnson, who's going to give us an update on the latest technology in arc flash mitigation. And before we do that, I'd like to run a couple poll questions as our habit and appreciate some feedback from the audience as we do this. So the first poll question is, how familiar are you with the National Electrical Code Article 240.87? No obligation or liability, strictly just getting some feedback from the audience to understand where their perspective is. A couple notes while we're running the poll question. A copy of the video and a copy of the slides will be available for download once they're posted to the website. You will receive an email notice when that's the case. Everyone in attendance will receive a certificate of attendance today. You don't have to do anything. That will come via email as well. Looks like we have a quorum on this poll. Here's how folks have weighed in on it. So good. We're going to cover a lot of interesting new ground for folks that are familiar with this regulation. And then the second question is, what is your biggest concern relating to arc flash instant energy mitigation? And again, this is a little bit farther along the thought process, but we do appreciate you participating. We will have a question. The presentation is going to last close to an hour, so we may not have time for questions and answers, but you're more than welcome to use the question entry box on the GoToWebinar control frame, and we'll get to it if we can. If we can't, we'll issue a Q&A follow-up that you will receive by email. All right, looks like we've got a quorum here. Here's how folks have weighed in on this one. Excellent. Excellent. Thank you very much for participating. Now I'd like to hand the baton over to our guest speaker, Mr. Austin Johnson. And Austin, you have the baton.
All right, thank you, Jim. I appreciate it. Just to introduce myself, I'm Austin Johnson. I go by AJ. I'm a product manager with Eaton for our low voltage assemblies, so low voltage switchgear, some of our switchboards, and then our high resistance grounding modules.
Austin, have you shared your screen?
No, I have not. I'm just doing a quick introduction. Don't have a slide for that. Let me go ahead and I'll get that pulled up so everyone can see it.
Thank you.
Just as an introduction, I've been in the industry for about 12 years now, really focused on the technical marketing side of things. I'm a registered engineer in the state of North Carolina. Given this presentation a couple of times, so I apologize if there may be some spots I speed up. If there are, just throw a question out in the chat and I'll make sure if I don't have a chance to answer it while I'm talking, I will certainly make sure I address it in the chat afterwards and get a response to you. Just as a quick note, all the material, that educational activity is protected by U.S. and international copyright laws. So reproduction, distribution, display, and use of the educational activity without written permission of the presenter is prohibited. Just a quick stipulation for there. EasyPower has everything that they need on their end, so they will have materials that they can distribute after this. But really, the primary goal for this is to go and dive into how you can understand how you can design and specify switchgear to be safer. One of the prompting questions that Jim was able to display for you was about the National Electric Code's Article 240.87. We'll dive into that in the presentation, but really what that focuses on is when you have a circuit breaker that is 1200 amps and above, one of the issues you run into is you start getting into instant energy levels to where you could potentially be in a zone where you do not have a level of PPE that is adequate. So there's a active requirement in the National Electric Code to put items in place to address and reduce instant energy where possible. And so that's where we'll spend a good portion of today's discussion. And at the end, the goal is that you're going to understand what the different methods are that you can use to meet Article 240.87, as well as some of the new technology. And when I say new, I'll preface it that you know, some of the stuff that we're talking about has been out there for 5 years and above now, but we are still running into folks that don't necessarily encounter it on a day-to-day basis or aren't aware of it. So it's still relatively new when you think about the electrical industry as a whole. So the first part is really want to dive into why this is a big ordeal and why this is important for people to have in the front of their minds when they're either looking at older installations that they may be replacing or just doing straight new installations from the start. Particularly as transformers themselves become more and more efficient, you have a higher likelihood of increased current available in the secondary, which that then leads to higher instant energy levels available with the equipment. And with that, there's a higher level of risk. So when we talk about a lot of the things that we're going to talk about with the newer technologies, we focus in specifically when it's an arc flash. We're not talking voltage faults. It's specifically when you have an arcing fault that's occurring. And so when that is happening, it's an electrical event where there's a lot of thermal energy that gets radiated out, convected and conducted in terms of heat. There's usually a bright light that's associated with it. The heat to it is substantial because what's happening is this is usually inside of electrical equipment. Typically it's copper bus is one of the main culprits. And when copper vaporizes, it's expanding by a factor of 67,000 in terms of volume, because it's essentially jumping straight from a solid into a plasma state. And as a result of that, you're going to see temperatures upwards to 35,000 degrees Fahrenheit, which can be just as hot as the surface of the sun. And along with, you know, the molten metal that's going out there, there's other components that go with it. And that includes, we talked about the light to where that's blinding enough. You know, you think about what you have to do when you're just doing welding and having to have a welding mask to block some of the UV light coming from the flames. Well, this is that to an even further extent. There's the burns associated with it. There's the shrapnel outside the molten metal, which can be generated at the same time because, okay, you think about the bus bar that's itself being evaporated at the time. Well, you're also building up an enormous amount of pressure to where like an enclosure can basically just become the same as a fragmentation grenade. So that's potentially being injected out with it. And along with all of this, you have what's referred to as the arc blast. And this is the pressurized wave that comes out of it. It's generally concussive force, and that concussive force can be strong enough to, you know, not only just fling a fully grown adult across the room, but it's strong enough to where you could potentially even see like a collapsed lung. So we talk about arc flash because the repercussions and the dangers of it are always present when electrical work's being done, no matter how safe you are. It's something you have to keep in the back of your mind that any given time, if I, you know, stop thinking about what I'm doing for a second, I'm not taking all the proper precautions, and, you know, there's always that risk there. So it's not necessarily meant to scare anyone. It's just more meant to, you know, there's a reason we continue to focus on this specific avenue, why we focus so much on instant energy, because it's all about lowering the risk and what the people that interact with electrical equipment are having to deal with on a day-to-day basis. So when we talk about things that can cause an arc flash, first, I'll point out that was a photo from an actual piece of installed gear. I still have no idea how in the world that raccoon got there, but it got onto the stabs of a low voltage power circuit breaker, and that's what happened to cause the incident that's shown in that photo. But animals entering equipment is always a risk. Usually it's not raccoons. A lot of times you'll see more snakes, you'll see insects, all trying to find a spot to be warm, and generally they'll build up, you know, spiders build up a nest, or you have wasps building up nests because it's a warm area, and then they can always bridge connections between two phases, and that's where all of a sudden now you've got an arc flash inside of your gear. It could be from test probes touching a surface that you don't mean to. Could just be a tool left behind or accidentally dropped into equipment. And there's other items, sometimes they can be due to negligence, but more times than not, it was just an accident that happened while energized work was being performed. And so when you look at when they happen, 10% of the time, it's when an operator is in front of switchgear or an enclosure and everything's sealed up. A quarter of the time, it's when there's no operator present at all, doors are all closed, but most of the time it's when someone is physically in front of the equipment doing energized work with doors open. So the goal is, you always want to follow safe work practices, but accidents do happen. And when those accidents happen, you want to hopefully have some engineering design into the equipment to try and protect you as best as possible. So I've mentioned incident energy a couple of times, but that's really what we're focusing on when we talk about 240.87. It's the amount of energy at a given distance that can be generated during an electrical arcing event. And that incident energy, the idea is that that gives you that way of gauging of, is my PPE that I'm wearing adequate? How big of an event am I looking at in terms of what's going to be dissipated? Because this is focused on the energy amount. It's not just a rating like you would say, like your total apparent power, like kVA, or your voltage or your current. It's specifically of what you're going to be exposed to, and the equipment is going to be exposed to if there is an issue. So when we talk about how we measure it, one of the things you may see is a warning label, similar to like what I have on the right side, to where it gives you two things. It's going to tell you what your incident energy is when you're within working distance, so typically anywhere between a foot to 6 inches. Most calculations, I think, tend to use 18 inches, which is a little bit over the 1 foot, but we want to make sure that's where we're measuring it at. And so like when you talk about things like arc resistant equipment, things that have had to go to a test lab and they have to have things measured to show that they're containing energy, that 1 to 6 feet, the 18 inches, that is essentially where they're putting the calorimeters and taking actual measurements in like test labs. But incident energy itself, there's a number of factors that go into it. If you're ever curious, you can always try to find yourself a calculator that's to the IEEE 1584 standard. That'll give you the ability to go through and see like, okay, what are all the different parameters that go into place to give me my estimations for what the incident energy level is. But the main things are, what is the rated voltage that you're working with? What's your available fault current? How far are you from where the arc is being initiated at? And then what is the clearing time to open and de-energize that circuit? So when we talk about low voltage switchgear, we're really talking about what's that main low voltage power circuit breaker that's upstream that is going to be able to open for us. And so the clearing time itself, when we're talking about breakers, it's not only how quickly can the system detect what or when there is an arc flash or when we have a rise in that current level, but then also for that circuit breaker then to go and perform its operation to where it can de-energize the circuit. And then just to give an idea, you'll typically see incident energy in one of two ways. It's either going to be presented as joules per centimeter squared, which I tend to see that more on the engineering side of things, less on the application side of things. When we're talking on the application, it's typically calories per centimeter squared. And so 1 calorie per centimeter squared is basically if you were to take your fingertip, put it over an open flame of like a candle and just hold it there for 1 second. So the amount of heat that you're feeling there, that is like that will be the equivalent thermal energy to 1 calorie per centimeter squared. And then just because it ties to several levels of PPE that are out there. So PPE level 2 generally will protect you up to at least 8 calories per centimeter squared. So if your body was to be exposed to that, that'd be the onset of a 3rd-degree burn to your bare skin with no barrier in between you and that amount of energy. But to go and highlight one of these. So one of the things I'll be bringing up a little bit later in this presentation is 1.2 calories per centimeter squared is kind of a focal point within the industry, because it's where you can basically get secondary burns to bare skin. So that is the reason that's a target is because a second-degree burn, while it's not pleasant at all, it's still something that someone can walk away from. not necessarily having to go and, you know, have like an overnight stay at a hospital. So that has become kind of a threshold throughout the electrical industry of where we want to try to get things, just so that way if someone were to be exposed, you know, say they didn't have the proper PPE on, as long as if they're getting hit with that level, it's still something they can walk away from. Is it going to be pleasant? Are they still going to be hurt? Yes. But the idea is that they can still walk away from it. They're not going to have to be carted out. They're not going to have, you know, potentially like skin grafts like you would at a 3rd degree burn level. They're all designed, it's designed to be kind of a, what's the highest acceptable level of damage to the human body that we're okay with if it has to happen. Ideally, you know, we could get this to where there's none at all, but unfortunately, physics, at least to my knowledge, hasn't gotten us to the point where we're able to get it down to where there is never the chance of there being always like zero risk to it, and the risk that's there being that low. So I believe we've actually got a revision this year, so I'm gonna have to update this presentation. I think it was 2024 now, but I assume this definition hasn't changed. But according to NFPA 70E, arc flash hazard is the source of possible injury or damage to health associated with the release of energy caused by electric arc. So we talk about the hazards. This is the formal definition that gets used within the codes and standards world. And you know, we've talked about a little bit, or at least I mentioned a little bit about PPE. You know, that's historically how folks protect themselves. It's making sure you've got the right rating on, and that when you're going out and doing equipment that the PPE you're wearing is still in good condition, because that's part of it. You need to make sure everything you're wearing is still good. It's been evaluated and checked recently. So that way, if you do have to have the unfortunate event happen to where you're exposed to an arc flash, that you know that equipment's going to do its job. So one thing that leads us into a lot of what we're trying to talk about today is that even if you're wearing a 40 cal suit, so this is the full space suit, there's still some risk of harm even if the event's significant enough, because that 40 calories per centimeter squared, we're really just talking about the heat exposure at that point. That's, you know, making sure your body doesn't get burned. But if you go back to that slide I presented with all the things that can happen during an arc flash event, there's still other hazards there that PPE really isn't going to protect you about. You may have protective eyewear on, but if that flash is bright enough and you're looking, unfortunately, like directly at the source when it occurs, there's still a chance that you wind up with some potential eye damage. There's still the concussive force that can occur along with the shrapnel. All these things are, you know, items that you can't really protect against outside of PPE unless you were wearing almost like a full, the same kind of suit they are using for if they were to try to go and disarm a bomb. But and even then, there's still risk even with those suits. So historically, and by historically I mean really since I would say the early aughts, when this first kind of came about in standards, the other way that can be that this can help you can protect basically personnel essentially is with arc resistant equipment. So when we talk about arc resistant in the US, we're talking about IEEE C37.27. That is the standard for arc resistant. Historically, it started in the medium voltage world, but has since then gone through a number of iterations to where now it's not only on low voltage world, it also applies to even motor control equipment. So it's not even just switchgear anymore. So within the arc resistant world, there's even different levels of accessibility and where you have your protection with, and that's usually listed as your accessibility type in your suffix letter. So as an example, one of the things that my line we've standardized on is we're always going to be considered type 2B. So that means you have arc resistant protection around the full perimeter of the equipment, and that's even with instrument and control compartment doors open. One of the things that I think tends to be misunderstood sometimes is that arc resistant protection it's not an always there thing. You have to make sure everything's secured, latched, and tight, because it has to contain all that energy and be able to redirect it away. So if something's not necessarily secured, you know, and a door can fling open, you know, you're not getting the benefit of that arc resistance there. So they're always, while it's a very sturdy design and does great job at protecting folks, you know, there's still some risk with it. If someone was having to do, say, energized work, for example, maybe they've got a circuit breaker racked out, maybe they're in the back dealing with the cable compartment. Either way, something is open to where, that arc resistant protection isn't going to really help you there if you have to do energized work, because it's designed only to protect when it's fully sealed, and it can redirect that energy internally out and away from the folks that may be around it. So then we take a look at okay, what can we do to potentially limit the hazard? So along with protection, really there's three things to look at. We talked about everything that went into an incident energy calculation. So if you look at voltage and available fault current, really the only way you're going to be able to modify those is if you potentially do a system redesign, or one of the exceptions with fault current is if you introduce current limiters. So those become much more difficult and complex to attempt to address within a system in terms of an engineering style control, because you're looking at a system redesign that may or may not even be feasible. You look at working distance. So again, if you're having to do live work, again, not much you can do there. You have to be in front of the gear. You're only going to be able to do that from a certain distance, and you're probably going to be within the restricted boundary. And again, not much you can do there. So really what that leaves us with is clearing time. So that's what has the most flexible, and that's what gives us the ability to work around with what the available levels are, because we can modify what that clearing time is. And as technology continues to evolve, I imagine the ability for equipment to respond is going to just improve further, and we'll see even better capabilities than what we can even see today. So now we'll dive into the National Electric Code, taking a look at Article 240.87. And so really what this states is where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted as 1200 amps or higher, then sections A and B shall apply. So what that really is talking about is when we look at section B, it's okay, how can we reduce the clearing time? And so that's what I want to really focus on. So with that in the list, there are really 7 categories, but you'll see there's a strike through on category 7, because that's really just kind of meant to be a catch-all for anything that hasn't really been around long enough, or there's not enough options out on the market to where it justifies having its own category. So it's more of a catch-all just for anything that could be developed in the future to help with this. So the first one is zone selective interlocking, ZSI for short. Then you get into differential relaying, which is the 87 functionality that you would see within a protective relay. Number 3 is an energy reducing maintenance switching with a local status indicator. So the name of that can vary by manufacturer, but typically it's, if you look at equipment, I think most manufacturers standardize it's got to be a blue light. So that's the one where you go up to the equipment, you say, hey, I'm putting you in maintenance mode, and you get a blue light on, and that's what helps out with that. Number 4 is the one that we're really going to spend our time on, because this is where a lot of the improvements and the focus has been made from a technology standpoint, and that's an active arc flash mitigation system. 5 is just your instantaneous trip setting. So that's, something that requires a little bit of calculation. I'll get more on that in a second. And then number 6, instantaneous override. That's something I'll cover a little bit, but unfortunately, for me, with low voltage switchgear, that's really only available on molded case circuit breakers. That is not available on low voltage power circuit breakers. So that's usually not even an option when you talk about low voltage switchgear. So diving into ZSI. So really what this does is it's relatively cost effective. Most of the time you're just using a twisted pair connected between breakers. It doesn't affect the coordination of the breakers, because it's basically communications between them to say, hey, who's seeing the fault, who's not, and to allow you to do really a super basic version of a differential scheme to determine where that fault's actually occurring within the system and speed up the reaction time of the breaker that is capable of clearing the fault in a given area. One thing that's, one of the biggest disadvantages is that there's not really a great indication of whether or not ZSI is connected, or if there's loose and missing connections. These days, I should probably have an asterisk on that, because as trip unit technology is evolving, that actually is becoming less of an issue, because most of the trip units now are having the ability to actually check on that. So that disadvantage is actually going away. But the biggest one is that you're really limited in how quickly you can react. Usually having only being able to get down to like 6 cycles or so, because you're dependent on the operating time of the circuit breaker. Differential relaying, I'm not going to dive into the specifics of it, but the idea is that, normally you got current coming in, you should have about the same amount of current going out, and you're measuring across different locations to make sure that all adds up to be correctly. And then, you've got an issue when, they don't equal each other. This is, still widely used within the industry. Depends on the situation, depends on whether or not you're going to implement it, mainly because a lot of times you have to have some higher accuracy CTs, you've got to do some extra wiring to get it all put into place. And then you're also taking up space when you're doing that, because sometimes the CTs that you need to use are not the smallest things in the world. But the idea is that you're doing this to, again, kind of figure out which breaker is seeing the issue, where the fault's located at, trying to isolate it, and only open up the breakers necessary at that point. 87 functionality tends to be pretty expensive to implement, so unlike ZSI, you are going to be paying a pretty penny for this one. And again, you're limited to the reaction time of your main circuit breaker to open and clear the fault. So there still are some limitations for it. The energy reducing maintenance switching, this has probably become the most prominent way of addressing energy within the industry. So the idea is that you've got a switch that's going to override whatever your current settings are on a circuit breaker, and it gets enabled essentially anytime you're going to have somebody either in front of the gear or working on the gear. So that way you can get a much faster tripping than you normally would, and it allows you then to greatly reduce your incident energy just because you're able to trip so much faster than you normally would. The downside of this is it's considered an administrative control, so you cannot leave it on all the time. I will say I have seen a couple of instances where that has not been abided by out in the field. They're lucky OSHA probably didn't catch them, because I'm pretty sure that would have been a red flag had they have come across it. But yeah, administrative controls basically are defined as you can only have that in place at the start of and then at the end of basically maintenance, or someone being actively in front of the equipment. Once somebody is done with their work for the day, that's supposed to be turned off, and you go back to whatever your standard incident energy levels are for a piece of equipment. The other drawback to it is you can sometimes lose coordination. So if you've got a selectively coordinated system, depending on what's going on with the person being in front of the equipment, you could potentially get some nuisance operations and tripping some things further upstream than was really necessary. If for some reason you experienced a large amount of inrush while you're in front of the gear doing the testing. The one that we'll circle back to, this is just kind of the high level for this one, and then we'll dive deeper in once we get through all the options. But number 4, the active arc flash mitigation system. There's a number of ways this can be implemented. There's several varieties and flavors that come when you talk about active arc flash mitigation systems. So the good news is, like most of these, you can use them regardless of whatever your arcing current is. So like, and I'm going to be kind of spoiling what I'm going to talk about on the instantaneous screen, but you don't have to actually know what your arcing current is going to be. You don't have to calculate that out and make sure you're exact. They can be used at all times, really. And then it doesn't affect the coordination of breakers, because it's detecting where the arc fault's at, and it's going to go and trip accordingly based off how the system's configured. Now, some of the systems have the drawback that they are still reliant on the upstream power circuit breaker, which that has some limitations in terms of how fast something can open. You can sometimes get nuisance operations. Not all systems have this issue, but some do, to where if they're a pure light-based system, when a low voltage power circuit breaker does its opening operation, it's elongating an arc through some arc chutes. So you're going to see some light flash typically in the gear. So if there's no way of if the system doesn't require any like current detection or anything like that, you could see nuisance operations from them. And then they are a little more complex. This is extra wiring, some more communications you potentially have to involve in your system. So along with that comes a little bit of the added cost. So there is that drawback. It's going to cost you a little bit more to implement this than, say, if you're doing something as simplistic as ZSI. So talking about the instantaneous trip setting. So for one, you can't do any temporary adjustments for this if someone's in front of the equipment. NEC does not allow that. It's really inexpensive. I would say most trip units today are ordered at least with LSI functionality. So you know that I standing for instantaneous means it's going to be there. The biggest thing is that you do have to understand what your arcing current is. So you have to go through, calculate that out, and make sure you have your settings programmed accordingly on your trip units. And then sometimes, depending on how your system's configured, it may actually bar you from being able to do selective coordination if you need to rely on this instantaneous setting. So one of the things to keep in mind in terms of the drawback of just relying on the historical method of just using instantaneous. And then, like I mentioned before, there's an instantaneous override setting, but that is something that is only allowed on multi-case circuit breakers. So unfortunately, a UL 1066 power circuit breaker, which is what you use in low voltage switchgear, that is rated to UL 1558. It's not allowed, so you don't even get this capability. Again, it has similar drawbacks as the instantaneous rating to begin with. You need to know what your actual arcing current is to program it. And again, you may be limited on whether or not you can achieve selective coordination. So if your system is considered selective coordination to be important to minimize downtime, it's likely not going to necessarily be an option for you. So let's circle back to method 4, which is our arc flash mitigation systems, and take a gander at what's in that. So if you look at a lot of the traditional methods that we talked about outside of the arc flash mitigation systems, they all kind of have the same drawback. They are all really dependent on that main circuit breaker. And when you look at a low voltage power circuit breaker, even without any delays, you could still see up to 3 to 4 cycles for it to go through its opening operation. So that ties into, we talk about clearing time. Well, that means your clearing time is kind of always going to have a floor that you really can't go past. And that's just assuming there's no delays. If you have delays, it's even worse. So for any system that's using them, particularly if there's a high fault current available, sometimes you could run into issues to where some of the traditional methods aren't really getting you to where you may be or where you'd like to be. So again, we talk about 1.2 calories per centimeter squared is really our sweet spot that we've been targeting. So it's potentially to the point where you may not even be able to get down that far. So that's what drives us to these arc flash mitigation systems. So there's multiple varieties out there, and one of the ones I talked about already is the one that you're still relying on that low voltage power circuit breaker to be part of your clearing time equation. So you still get the limitations that all the other methods do. So instead, we start looking at, okay, what do we do when we can take that out of the equation? How do we speed things up and have a faster acting device that gives us that much shorter clearing time, which then means a much lower incident energy level? So the first one's the bolted fault approach, sometimes called a crowbar system. So some of you may be very familiar with this. Crowbar systems have been around for quite a while. The idea is that basically they're going to if anytime an arcing fault is detected, it's going to initiate a bolted fault essentially within the system to spike your current up, which will then cause things to trip even sooner. So the device itself can react anywhere between 2 to 10 milliseconds. So that's a lot faster than what you'd be looking at if you're talking just like a short time rating of a low voltage power circuit breaker. But one of the limitations of it is because you are doing a bolted fault operation, that also means you're drawing the peak fault current. And with that, you get all the forces that occur inside of gear when you're experiencing such a high amount of current in the gear. So that's potentially you're damaging like bus bracing. You're going to see metal getting bent again from the magnetic forces that occur when you have such a high fault. So there's potential of, while this does help you and protect personnel, you're still working in a situation where you're also potentially damaging your equipment to where, okay, I went and I mitigated the fault, but now I still have to go and do a full replacement of my gear. So the idea is like, okay, well, what can we do if we had a current limiting version of that, essentially, to where we can extinguish the arc within the system, but doing it without having to draw the peak fault current like you do with the previous style on a crowbar style. So that's where we want to focus in, and usually what that entails is that has us pulling in what you can see down there in our blue box, was what because that's how we'll refer to a lot of things for this discussion, is our arc quenching device. You'll be able to see variations of this through different manufacturers. Generally, the word quenching or quencher is the common terminology that's used around the industry. So you'll be able to find this among several manufacturers that at least I'm aware of, and they all provide similar solutions. They just approach them in slightly different ways. But really, how an arc quenching device works is it's detecting that arc through some light sensors, and there's also line side CTs. And once it's detected that, hey, we do have an arcing fault going on, it's going to send a trigger to that arc quenching device. And then typically, the way that at least it seems to work throughout the industry, so I know, like I said, there's multiple groups, they all seem to have the same end game. It's how they get there. Sometimes that will vary, but the idea is that they're going to have a lower impedance fault inside their quenching device that allows for the arc to be drawn from wherever it's occurring inside of the gear into that quenching device, extinguishing it in the gear. And the idea is then that our quenching device is able to maintain the arc until the main breaker can actually open and de-energize the lineup, taking the fault energy completely out of the equipment. So the way that when we talk about a quenching device, at least from the Eaton perspective, the way we do it is we actually have what we call our 2 arc containment vessels, in which the 3 phases are connected up. And then we have a wire that sits across some contacts. And basically the wire itself is run as taut and is only on the B things. But once this thing has a signal that's sent to it, it'll discharge some capacitors. Those capacitors will then send energy across those contacts. And then because of the phase angle difference between the 2 contacts, there's going to be Lorentz force that generates across that wire, which is getting the discharge on it, allowing it to then create a short between the 2 phases. And that's where the arcing then gets maintained between those 2 contacts until the low voltage power circuit breaker can de-energize. So just to provide more of a visual of kind of how things would work, that's not meant to show, and I realize this graphic's a little off, but really you have individual phase CTs. It wouldn't be a window style CT. This was just how PowerPoint allowed me to get this set up. But an arc quenching system works is initially the arc flash is detected by light sensors and CTs. And it's important, and I'll highlight that we say both light sensors and CTs, because that's how you avoid that nuisance stripping. It's not just the light detection, it's also the inrushing current. There's also the fact that you have light coming in from an arcing event and that you're getting a blocking signal from your breaker just to make sure it's not actually the breaker that you're seeing. So like if you had like an overload on a long time delay that your breaker's picked up, it's now opening, so you do have higher than normal current. That would be detected by your CTs. So you still want to have that blocking signal going from the breaker that says, hey, I've got this, we don't need you to operate, this is a controlled situation. So that all that verification really takes place in under 4 milliseconds, and that's when the signal has, and part of that time also includes the signal to the arc quenching device, allowing that arc quenching device to create that low impedance fault and pulling the flash out of the system. And then again, it's designed to sit there and hold things until your main breaker can go through and open, and that's where that 67 milliseconds is coming into play at. So talking about some of the benefits, really the biggest piece is that reaction time. Talked about how much of an influence the total clearing time is for a system, and for how much that can have an impact on what your incident energy rating is. That is really the key, is it comes down to the time piece. And the benefit of it is when you have an arc quenching system is you may actually wind up with lower PPE requirements, and you may have reduced arc flash boundary. So if you have equipment that is, I would say in a high foot traffic area to where you're gonna have a lot of folks walking through, that's something to keep in consideration, is that you have this and it's gonna reduce where you have to lay out your boundaries out, like on the floor for where somebody is allowed to walk. There's also the fact that it reduces what kind of damage you could potentially see within switchgear. So, you know, I'll stay on hands. Switchgear lead times are still relatively long right now, so that this has been a focal perk for me when talking with folks on one of the reasons you want to have something that will prevent you from having to fully replace your lineup is, at least in this day and age, it's going to help you at least have to avoid some of those longer lead times that have been causing heartburn. In the US, there's been some discussion about this. I actually got to present a white paper on this last year. And there was also another one by one of our competitors kind of talking about the same thing. So within the IEEE world and the UL markets, there's not really a good standard that talks about arc quenching and arc mitigation style systems and what they can truly do. So instead, we actually have to test to the arc resistant standard using an active component instead of like the passive construction like you would see for most systems. Now, hopefully, over the next couple of years, that'll evolve a little bit, and we'll be able to create kind of a new standalone standard, similar to like what's in the IEC world. Because in the IEC world, you can't qualify arc quenching as arc resistant. They have to; those are actually two completely separated out standards and requirements. So I'm hoping we'll eventually be able to do something similar, so we can show like the true advantages in terms of what an arc quenching system can do. One of the other upsides is it's less space that you have to take up with. So when you talk about an arc resistant system, there's usually going to have to be some venting, whether it's done with some plenum, or if it's ejecting solely in the air, you have to still have at least like a 10-foot high threshold, because you do have to be able to take that energy that is built up inside of the equipment. You have to be able to safely get that outside of the equipment without necessarily harming personnel. So there's some construction pieces that have to go into play when you're looking at arc resistant construction. We talk about an always on system. So unlike the maintenance mode, which is an administrative control, this is something that can always be on, not just when someone's near or in front of the gear. And because of that, whenever you experience an issue, you end up having less stress overall on your system, just because, again, you're not necessarily going down the same route of having to do a bolted fault where you're pulling in the maximum amount of current. So just to give an idea of scale, so if you had a 600 volt 100 kVA system, and some of you may be sitting there like, well, I'm not in Canada, I don't have to ever deal with 600 volts, I only deal with 480. Still kind of the same precedent. You're still going to be dealing with quite a bit. You'll still be probably above 100 calories per meter squared when you're talking about instant energy for a system. So looking at this, the short time rating, you know, you can see the scale of just how all of these different types of instant energy reduction methods come into play and just automatically have scaled down what the risk is of being in front of a piece of equipment. And then if we go a step further and we take out that short time rating from skewing our results so much, you can get a better idea of how different options kind of stack up against each other. And you can see where arc quenching switchgear is, it's below that magic number we talked about, of that 1.2 calories per centimeter squared level. On average, the value you see there, that was actually measured from test results actively in a lab with these values going to play, where 0.8 was the maximum. It wasn't even the average. It was the maximum of what was seen during an event. I would say our average was actually quite a bit lower than that. But this gives you an idea still, even if arc quenching doesn't necessarily make the most sense for whatever your installation is, or what your budget limits or your installation requirements are, it still gives you an idea of just how much you can reduce incident energy even with these other methods. So ultimately, it's going to come down to like what's going to make the most sense for what your project is, what your equipment is, and what you're having to walk through and deal with. So just to circle back and reiterate, talking about clearing time and instant energy specifically, you know, instant energy is going to be directly proportional to how long your arc fault's being allowed to run wild and rampant within the gear. And then obviously, if you can reduce the amount that the arc fault lasts, it gives you lower incident energy, which means you're going to see less damage, there's less risk to your personnel, And then ultimately it should be lower downtime for what you have to work with after an event. So with that, I've got, again, I always say I talk fast, so I did want to make sure I did leave some time for questions, because I don't know how well it will be able to connect necessarily after that. But just to kind of give you a quick and easy recap, I did see the question that came through that Jim was able to answer about the presentation. So there will be a version of this available to you afterwards, and it'll have this table. But this table is just to give you an idea of what you're looking at when you're talking about the different solutions. So if you just talk about basic switchgear that you can find here in the US, that's just your UL 1558 metal enclosed low voltage switchgear. Once you start talking about arc resistant and arc quenching, that's when the IEEE C37.20.7 comes into play, and then really the differentiators between them. So arc resistant, you've got a passive system. It's solely focused on personnel protection and getting the energy away from anyone that is around the equipment. And then you move to arc quenching switchgear, which is your active system. The idea is that this reacts much quicker. Most of the time, it's going to lead to protecting your equipment, not just the folks that are around the equipment, and potentially even reduce downtime. And then there's the crazy, if you want to have both versions, both a passive and an active system in place, that is certainly available. So with that, I was trying to get us at least where we still had 10 minutes. I'm a little over that, but we'll go ahead and move into whether or not there are any questions.
Yeah, AJ, William had a question regarding the blue light on a maintenance mode unit. Is that required?
There is, and again, I can't remember if the blue light is specific standard. I know that's our internal standard. I know there is a requirement to have an indication that the maintenance mode is active. What I have shown here is what's displayed on the gear. Typically, you will also have an indication that is local on your power circuit breaker as well. So as an example, this is specifically an Eaton trip unit, but I believe it's the same situation across other manufacturers. This actually isn't normally a blue ring. This is actually a ring that lights up. So when it's on, that will actually turn blue, and that is your indication that the maintenance mode is active. So there is a requirement, I believe, in the standards for the maintenance mode to have an indication. I just don't necessarily remember off the top of my head whether or not, it says it has to be blue. It's just but there does have to be a way to indicate that maintenance mode is on for personnel that are near the gear.
And then the follow-up is William's asking, will you please explain why the instantaneous override is not an option in our circuit breakers?
I couldn't tell you 100% for certain. I believe it ties to it ties into the build requirements in the UL standard. I'm not the best person to be able to speak on that, but I believe it has to do with the UL standards that it's in UL 489 for molded case circuit breakers, but it is not. It's either not allowed or there's no testing methodology for it within UL 1066, which is the standard that power circuit breakers are qualified to.
So this is a question from me. Once the system has been exposed to an arc flash and everything worked, how much has to be replaced due to the arc itself?
So it will depend on your system and what it is doing. At when I'm speaking now, I'll speak specifically to our system, since that's really the only piece I'm really qualified to speak to. For our system, it would require someone to go out, look in the gear, for one, identify what caused the arc, what initiated it. Most of the time with an arc quenching system, you typically will just have to clean up some bus bar wherever you might see some flash marks on it, because it's usually so quick that nothing really actually burned up. It was just more of you'll see like a char streak on some bus bar. And once it's been cleaned up, it technically can be returned to service there. The way our specific system works is our arc quenching device is a one and done style. So after an event, you would have to take our little blue box here out of the system. Say, for example, you do not have a spare on hand though. We do have the way for you to be able to return this to service without the arc quenching device. As a result, though, you will not have the capabilities of the arc quenching system. So when we talk about the labels, find the right slide for it real quick. Where you at there? So one thing you'll typically see on our labels on our arc quenching system is you'll actually have two ratings. You'll have one when you are protected by the arc quenching system, and you'll have one when you're not. So if you didn't have that spare on hand, you would still be, you basically will have that, whatever that unrestricted incident energy level is, which will be fairly high. So that's just one thing to keep in mind is if you didn't have the spare, you could still be up and operational. You just won't necessarily have the protection on it. And one of the things that I didn't really cover, because again, it's specific to our gear, and I try to keep this as generic and open as I can for learning purposes, because the idea is I want to focus on the technology, not really our specific solution. But you can see here on this illustration that there's a little light here. That is the arc quenching system active light. So for our gear, if that light should always be on. If for some reason there was an issue with the arc quenching device or the arc flash relays or something else, or it's done its job, that light goes off. And then that is the signal to an operator that says, hey, if you're going to approach this, you need to make sure that you're wearing the appropriate level of PPE for that higher level of incident energy, because something has gone on to where that system is not active anymore and you no longer have protection or reduced levels.
Good. There is a request that someone in the audience would like to have a link to the white paper that you presented. Is that something you could supply or direct them to?
I will try to get you a link for it afterwards. I have to go find the IEEE link because that was presented at ESW, so IEEE has the full ownership of that white paper. But I will try to find, I'll paste both of them, the one that I was a contributing author on, as well as the one that I know one of our competitors wrote, where again, it was talking about similar subjects, about the need to have kind of a new standard here within the US that's focused more on the arc quenching side of things versus being so dependent on the IEEE arc resistant standard. So I'll look and see if I can find those links after I stop presenting, and I can try and post them in chat.
All right, thanks. And then the last question is there a specific arc flash relay that's recommended for use on the primary or the secondary of the transformer?
It'll vary by manufacturer. I mean, for our system, we certainly have stuff that we recommend because that's what we build with. But I'm not going to be here and try to do anything from a commercialization standpoint. There's a number of manufacturers out there. Most of them I would say, operate fairly similarly to where they're going to be focused on anything internal to the piece of equipment they're installed in. You may find some systems to where they would traverse out to maybe into the transformers, and there may be some that differ from the low voltage to the medium voltage world. But at least a lot of the ones that are light-based, they all have fairly similar construction requirements to where there's a module looking at some kind of a sensor that's there to gather the optics to send that relay back. But I'm not going to say there's one that's better than the others. I would say they all operate fairly similarly.
Well, AJ, that was an excellent presentation. I think we've answered all the questions. And we certainly do appreciate the time and the presentation. You did a great job.
All right. Well, I appreciate everyone sitting and listening to me. And I don't know if Jim, if you provide out my email or not, but folks I'm always open for anyone that wants to learn more or get any more information. And like I said, I'll try to get those IEEE papers as well, just so if people want some more educational material, they can have it.
Good. So yes, this is your, let me show your email address.
Yep.
Thank you very much.
Yep. All right. Thank you.
Have a good day.
Everyone have a great day. Thanks.